Welcome to today's U.S. Clean Energy Challenges Focus on Hydraulic Fracturing webinar, sponsored by the American Academy of Environmental Engineers. At this time, it's my pleasure to introduce today's speakers. Our first speaker is Hunter Nolen. Mr. Nolen is President of Industrial Services at CDM Smith Incorporated. He has 30 years of experience in managing environmental and infrastructure design, construction, and operations programs for a broad range of industrial and public clients, including scores of projects in the oil and gas arena. Since the very early stages of the shale development boom, Mr. Nolen has been actively engaged in providing environmental and infrastructure solutions to help assure environmentally responsible development activities. Projects have included design and construction of multiple produced water and frac flowback water treatment systems, environmental impact analyses, basin entry planning services, and design and construction services for well pads and supporting roads, ponds, and related infrastructure. Our second speaker is Kevin Rice. Mr. Rice is the Senior Business Development Manager at Baker Hughes. Mr. Rice has over 16 years of experience in the oil and gas industry with roles in field operations, engineering, manufacturing, sales, marketing, and operations management. From an initial focus on completions, he has furthered his knowledge to include drilling and evaluation, completions and production enhancement, including hydraulic fracturing. Our third speaker today is Tomastik. Mr. Tomastik is a geologist with the Ohio DNR Division of Oil and Gas Resources Management. Tom has over 30 years of experience in the oil and gas industry. He's responsible for all of the underground injection control duties. As part of his work in the UIC program and in cooperation with Ohio EPA, he reviews renewal permits for Ohio's existing Class 1 wells and for permitting and installation of new Class 5 wells. In addition, Tom also conducts highly complex groundwater conflict investigations involving oil and gas contamination and industrial aggregate mineral dewatering operations. And our keynote speaker today is former Colorado Governor Bill Ritter, who is currently the director of the Center for the New Energy Economy at Colorado State University. Mr. Ritter was elected Colorado's 41st governor in 2006. He quickly established Colorado as a national and international leader in clean energy by creating a new energy economy and tripling the state's renewable energy standard. In a state with substantial fossil energy as well as renewable energy resources, Governor Ritter created policies that balanced energy production with protection of air, land, water, wildlife, and communities. At this time, I will turn the program over to Hunter to begin.
Well, thank you, David. On behalf of the American Academy of Environmental Engineers and Scientists, it is my pleasure to welcome you to this webinar on U.S. Clean Energy Challenges, focus on hydraulic fracturing and oil and gas development. My name is Hunter Nolen, and I serve on the Board of Trustees of the Academy. Since 1955, the Academy has served the profession by providing the opportunity for testing and board certification of environmental engineers and more recently environmental scientists, in much the same way as the medical profession provides board certification for its specialists. In addition, the Academy bestows internationally recognized awards, recognizing outstanding projects and individuals who have made significant contributions to the profession. Among its many functions, the Academy provides seminars and workshops on topics of significance in environmental engineering and science, with this webinar being one example. Many thanks to the Academy's Seminars and Workshops Committee for organizing today's discussion, and especially Ms. Wendy Work, who effectively directed the compilation of this webinar. I encourage you all to learn more about the Academy by visiting its website, which you can see the address at the bottom of the screen, AAEE.net. I'll start out this presentation by giving a general introduction to shale oil and gas development and some of the environmental challenges that go with it. And there are really four aspects to my presentation. Number one, I'll give you a summary of the shale resource as we know it today. Second, I'll talk about some significant economic and geopolitical implications that this new arena brings. Third, some environmental concerns that must be managed in the development of shale oil and gas. And finally, speak to this new arena in terms of what it means with respect to overall energy choices. Let's start with world energy consumption and what is expected to occur over the future, the near future in this regard. As you can see on the left-hand side of the screen, energy consumption is going to grow in the neighborhood of 40% between now and about 2035. And what you can see in the red there is that much of that growth is from countries that are in their development stages. Developing countries are in, or the developed countries are in blue, and the developing countries are in red. So there is tremendous ongoing growth in energy demand throughout the world, and this is anticipated to continue at a very substantial rate. On the right-hand side of this graphic, you'll see the sources of the major aspects of energy production. Liquids being at the top, coal following, natural gas, renewables, and nuclear. Now, I think we'd all like to see renewables with a steeper curve to begin to have a much more of a significant total footprint in terms of our energy provision. But in reality, we still will and rely on major energy sources from traditional hydrocarbon sources. What I will speak to today will be focused primarily on the new arena of shale, oil, and gas in this regard. In the United States, we utilize a great amount of energy, as I'm sure you all know, and almost 50% of that is imports. This was a 2010 graphic. The latest information I've seen is that import has reduced to about 40%, which is very good news, and I think largely related to the new findings in shale gas and other sources of energy in the United States. So we would like to see that continue and to reduce the amount of economic export that goes to energy usage in the United States. And it's not going to get any easier. Here's an example graphic, China. On the right-hand side of this graphic, you see the number 14.3. That's 14.3 million barrels of oil equivalent expected to be utilized by China in 2025. And at the bottom of this graphic, you see that at that same time, they expect to produce about 5 million barrels a day. So that equates to about 3.4 billion barrels a year that China will have to import to meet its demand. And that creates even greater and greater worldwide competition for this precious and limited resource. Now, we've had a very substantial change in the development of oil and gas here over the last few years, especially since about 2000. Traditionally, over the history of oil and gas production, most oil and gas has been captured from reservoirs underneath fields called traps. So access to oil and gas primarily over the history of oil and gas production has been oriented towards finding these so-called traps and placing wells within those traps and recovering oil and gas. And these are typically very high permeable zones that produce oil and gas fairly readily without any particular manipulation of the formation to make the oil and gas flow. Well, as we have used more and more oil and gas over the years, we've had to go to deeper and deeper water to find such conditions. We've had to go to far places in the earth, around the world, to find such conditions, and it's getting more and more difficult to access this kind of conventional oil and gas location. Now, if you look at the bottom right-hand portion of this graphic, you'll see a green area that says source rocks, which generate oil and gas. Historically, the source rocks have not been accessed to actually, it's been the traps that have been accessed. Well, with new technology, and in particular horizontal drilling, hydraulic fracturing, now have access to these source rocks where we can readily and economically develop oil and gas from those source rocks. That opens up a tremendous amount of new energy for development, which previous to just a few years ago, wasn't available. So here's what's happening. On the upper left-hand side of this graphic, you can see a gentleman looking at an outcrop of shale rock. Shale rock is a very impermeable rock. It's got fractures, natural fractures throughout it. But gas is trapped, oil and gas is trapped within that shale rock, and it doesn't naturally flow very readily at all. It's trapped, and therefore if you were to put a well down into that material, you might show a little initial oil or gas, but that would dissipate very quickly, and you really wouldn't be able to produce out of such rock. What you see below that graphic is a piece of shale rock that has been placed in a glass of water. You can see bubbles coming from that rock, and that represents natural gas, which is in place throughout this rock. And so one can understand that what's required in order to get gas and oil to flow from such material is fracturing. In other words, increasing the surface area that's available for these materials to flow out of this rock and make its way to wells for collection. The right-hand cartoon graphic is, you can see the ground surface, and you can see some wells that go down to the shale material. And what you see is laterals. At each well location, you see laterals that go out horizontally into the rock. And those laterals can be quite long, typically a mile or so, sometimes even longer than that. 6 to 8 of these laterals in a single well location. And those laterals are hydraulically fractured so that surface area is created for the material to flow to the well. And then there are other things that are done, such as adding the sand or other proppants to hold those fractures open so that the oil and gas can continue to flow to the well. Fracturing has been around for a long time. It was initially started way back in the late 1800s using explosive fracturing. First hydraulic fracturing happened in the late 1940s. By 1988, it was common practice. And then in the late 90s and in the early 2000s, there began to be a lot of investigation and utilization of the technology in a shale area down in the Fort Worth area in Texas called the Barnett Shale. And a company called Mitchell Energy and Devon Energy joined forces and really developed the ability to combine horizontal drilling, hydraulic fracturing in a way that made development of gas, in the case of the Barnett, economically successful. And since about 2006, this technology has really taken off in development of oil and gas from shales and other not permeable formations around the United States in particular, but also beginning to be applied in various places around the world as well. So today, in 2012, really many wells, 60 to 80% of all oil and gas wells are typically hydraulically fractured, somewhere in the neighborhood of 35,000 per year, 2.5 million to date, was the last data that I've seen. So you can see that it's a readily utilized technology. The production of natural gas from shale, as you can see, has really taken off since about 2006, when the advent of isolated multi-stage fracture stimulation of horizontal wells really was developed again in the Barnett. So various formations around the United States began to be developed in this fashion. You have the Barnett in gray, Fayetteville in green, and various others in different colors. So what you can see there of particular note is very major growth of development, natural gas, and of course oil as well in these shales formations. And of particular note, there's been a tremendous amount of success, especially recently, in not only getting natural gas to flow to wells using these technologies, but a lot of oil is being developed in this way as well, in formations that have both gas and oil, and natural gas liquids too. There are quite a number of substantial, unconventional shale, tight gas, and other basins throughout the United States that are being approached in this fashion. Many of you have heard of the Marcellus in the Northeast. We have the Eagle Ford in Texas, and lots of areas in the Rocky Mountain West that contain a tremendous amount of natural gas and oil that is now accessible using this technology. And one of the results of this boom is that geologists are really beginning to understand and spend more time, energy, evaluating truly how much of this resource is available to us from these source rocks. And there's a process of developing technical reserves, estimating the reserves of oil and gas available that are technically recoverable in various formations. And as more and more has been learned about these shale formations, the quantity of the estimated technical reserves has really expanded tremendously just in the past few years. So what we are faced with is the recognition of a tremendous resource available in the United States, throughout North America, and really throughout the globe, previously not available to us, which changes many aspects of energy development. And we're in the midst of the very early stages of experiencing and observing and dealing with those changes. Now, currently there are a number of very significant known sources of shale around the world as well, but very little of the world has been studied, and so there's much more that is unknown about this resource globally than is known. So I think we can expect for there to be a tremendous amount of development around the world. We're already seeing it in some places like Poland and other locations where countries are recognizing that they now have ability to develop their own oil and gas, whereas they previously may not have. So we can expect to see, and we have begun to see, a major global development activity around shale and other unconventional sources of oil and gas. So what does a trillion cubic feet of gas mean? Well, 1 trillion cubic feet of gas is enough to heat 15 million homes for a year, generate 100 billion kilowatt hours of electricity, fuel 12 million natural gas vehicles for 1 year. The Marcellus alone, which is an area in a portion of the Appalachian Basin in the northeast United States, is estimated to have between 50 and 500 trillion cubic feet available. So you can get a sense of the magnitude of this resource that's available to us. And recent estimates suggest that this represents a 120-year supply for the United States. And as I mentioned previously, there's a whole lot of oil and natural gas liquids that are being developed as well. Now, this brings some significant economic and geopolitical implications that are very recent and very significant. Many of you may have seen the Time magazine article, "This Rock Could Power the World." Interesting article that was presented in Time. So what are some of the characteristics of natural gas? Now, you'll note that I am focusing more on natural gas than oil and natural gas liquids because of some of the very significant changes that the large quantity of available natural gas now brings to the table for us. Well, we know we have a lot of it. It used to be considered an unreliable source, and so you didn't see much use of it in power production. In fact, there was fear of using it for power for many years because it was needed for residential heating, et cetera, and there was intent to protect residences from having to compete for natural gas with power companies. Well, that's changed considerably. It is the cleanest combustion fuel available. It produces about half the CO2 of coal, but it does have to be managed, especially fugitive losses, because methane released directly to the atmosphere is more potent, considerably more potent than CO2 from a greenhouse gas standpoint. It is considered a very, very important bridge fuel for eventual long-term transition to renewables. And it's also a very, very valuable leveling fuel for renewables. For example, wind, you can't get wind power when the wind is not blowing, and solar, you need the sun to shine to collect solar power. So during those periods when wind and solar and other renewables are not meeting demand, natural gas is a very effective leveling fuel for that purpose. In the United States, we already have a very extensive transmission and distribution network, which makes it readily utilizable throughout the U.S. And it's underutilized currently in power generation. MIT recently suggested that we could increase our utilization of natural gas in the United States, achieve 20% CO2 emissions reduction very rapidly based just simply on existing facilities that can burn natural gas. A very significant point also, current supply far exceeds demand. Now that we have access to all of this gas, we have more of it than we have infrastructure that can readily utilize it in the immediate term. Many people are recognizing the importance of it, not only oil and gas companies and many in the public, politicians are as well. For example, the White House has recognized the great value that this resource brings to our society. The White House published a 3-point plan, developing a secure America's energy supplies, energy reduction, and innovate clean energy being key points within that plan. And a recognition that natural gas and oil from shale formations will play a critical role in domestic energy production in the coming decades. Let's look at supply and demand and the meaning of this just in terms of price. A barrel of oil is north of $90 a barrel, and about a million BTU of gas is around $2.50 a barrel. And these numbers, of course, change over time, but that's generally accurate today. And 1 barrel of oil equivalent of natural gas, 1 barrel of oil equivalent is about 5.8 million BTU. So the price of 1 barrel of oil equivalent of natural gas is about $14.85, using these assumptions on the price of a barrel of oil here and a million BTU of gas. So compare $97 to $14.85 for the same amount of energy. And what that translates to is a major driver, economic driver, for expansion of utilization of this large natural gas resource that we now have available. Okay, so what you see here is a rather complex graphic, but in simple terms, on the left-hand side, you see various supply sources, petroleum, natural gas, coal, renewables, and nuclear, with roughly their magnitude of availability. And then on the right-hand side, you see demand sources, transportation, industrial, residential, commercial, and electric power. And I've circled a couple of areas where natural gas is utilized for transportation for only 3% of the total energy required for transportation, and only 18% of the total energy used for electric power. Both of those areas represent very substantial areas where there's opportunity for growth. And what you can expect to see is much more orientation towards natural gas-powered transportation sources and much more orientation towards natural gas power generation. And there are very substantial economic implications to this new find as well. Let's start with the U.S. reliance on foreign oil and gas equates to about $500 billion in wealth transfer annually. Big number, very significant if we could keep that number here in the United States. The Barnett Shale alone, this area of near Fort Worth, Texas that I mentioned, which was the first significant shale area, it's estimated that $11 billion and 111,000 jobs were annually contributed to the Dallas-Fort Worth area, plus about $275 million annually in state severance taxes. The Wall Street Journal, probably about a year ago, suggested that there had been over 600,000 jobs created to date in the shale gas arena alone. And the U.S. chemical industry is getting a rebound from this event as well because of the source materials that shale development provides for chemical production. So it's anticipated there'll be $132 billion of U.S. economic output over a period of about 10 years, and 400,000 jobs in the chemical sector. So these are just some examples of the significance of this finding with respect to the economic influences that it can have here in the United States. And geopolitically, you also see that big oil is really focused in new areas. Previously forced to be in places that may be very dangerous and risky to develop, and now they have the opportunity to focus much of their energy in development in areas that are safer and easier to address. So a big shift in oil and gas development orientation, companies' orientation towards the United States, North America, and more stable parts of the world. Well, there are environmental concerns related to any and all oil and gas development, and the new hydraulic fracturing and horizontal drilling is no different. It has environmental concerns that must be managed. And these concerns can be categorized really into two categories, surface and subsurface. From a surface standpoint, air emissions, water resources and quality, land impacts, drilling locations, infrastructure, truck traffic, lots of truck traffic, things of this nature. From a subsurface standpoint, protecting underground water resources is a very important matter, and some implication of seismic events that can be triggered with respect to disposal activities of liquids underground. And this is an area that's receiving some interest. I encourage anyone who wants to look at that any further to access the USGS, the United States Geological Survey. They're engaged in studying this. In fact, there is a presentation available on the Academy's website by Dr. William Lyas, who gave a presentation at an Academy function several months ago on seismic events. And in essence, the USGS represents that there may be some relationship to some degree, although that risk appears to be very low and manageable. But I think it's an interesting area of concern, and people should continue to study it and understand it. There is a very extensive regulatory framework around oil and gas development, and including the unconventional shale development. There are lots of federal regulations that apply to protection of the environment. State regulators are typically responsible for oil and gas permitting activities, et cetera. Have local and regional authorities that implement local regulations that drive various actions, and you have a number of independents who are providing input to regulations. And because of this very rapid change and development in this arena, there is a lot of interest and a lot of focus in the regulatory arena. And there's quite a bit of development. There's a lot of flux occurring in the regulatory arena, and a number of very significant studies going on, such as EPA's hydraulic fracturing study, which is in progress right now. Now, one of the significant aspects of hydraulic fracturing, of course, is water use and potential implications to environmental impacts that might bring. Frack water utilized is somewhere typically between 2 and 6 million gallons per well. There are additional components that are added to the water to make the fracture behave the way that the operator need it to behave. And then there's what's called flowback. When a well has been fractured, the water that was pumped down to do the fracturing, much of it returns is returned and pumped out of the well, and that has to be handled as well. The water is a very, very significant aspect of successful development of unconventional oil and gas. One has to find it, transport it, store it, treat it, lots of reuse, there's disposal required of it, much effort required for protection of it, and that's both surface and groundwater. And all of this means that there needs to be very effective and thoughtful planning around the water cycle in oil and gas development especially in the unconventional shale arena. And that planning really exists for both oil and gas companies, regulators, and the public that is in the location where much of this development is occurring. Now, we should understand the implications of shale in terms of water use and how that compares with other major water uses. And in reality, even in areas that are receiving a great deal of development, the overall usage of water is relatively low compared to other major uses such as mining, public water systems, other industrial and power generation. But it still creates an added stress, and in some areas, for example, drought-stricken zones like South Texas, or other areas that are in highly sensitive environmental conditions with the ecology and public protection concerns, it's still a meaningful use of water that needs to be managed, but it needs to be managed with the proper context of quantity. And it also needs to be understood from the standpoint of, well, how much water does it take to produce shale gas, shale oil and gas, versus other forms of energy production. And in reality, it's a relatively small water footprint compared to many other sources of energy production. And that should be understood as well. So for protection of water quality, there really are three primary areas of concern and attention. Number one is surface activity. You have spills, you can have dikes that breach, and all of these things require ongoing attention. And a lot of attention is being given to the management of surface activities for that reason. You have folks that are concerned about release of fracturing fluid to drinking water aquifers. Most people in the know and who really understand the technology is a minimal or even non-existent risk. We'll have some other speakers today that can speak to this in a little bit more detail about why that is. But it's still a concern that certainly the public has quite a bit of focus on, and EPA's hydraulic fracturing study is, of course, spending a good bit of time on that matter as well. But it's important to separate the science from the fear in that regard. And there's a lot of attention and emphasis on that matter. And then, of course, there's well completion. A well has to be properly completed to protect various zones, drinking water zones being one. And the next speaker will spend considerable time on that matter. Now let's just talk about energy choices overall. The sources of the world's energy are basically distributed in the following way. Oil is over 33%, coal is at almost 27%, natural gas at about 21%, renewables a little over 10%, et cetera, nuclear and others included. There's a nice quote by Klaus Lochner. There are very few energy resources large enough to cope with modern global energy demand. Any technology is able to satisfy these demands will unavoidably interfere with natural dynamic systems, which must be mitigated. A scenario in which available energy resources fail to provide a basis for the energy infrastructure will be a scenario with drastic reductions in economic output and one in which living standards will fall back to much lower levels. So as a society, we really are faced with, we need energy. You saw earlier how the demand is growing, and it's up to us to find ways to manage our growth in energy demand while managing the environmental impacts effectively. And as you can see, there's lots of opposition to all kinds of energy sources. We really need them all, and we need to effectively manage the environmental consequences of all of them. And so from my perspective as an environmental engineer, what we're faced with is the need to accomplish environmentally sound shale development. And there are lots of influencing factors to doing this, but primarily four in my mind. There's the oil and gas companies who have the expertise to go acquire access to oil and gas with water expertise, but limited water expertise. We have the community that needs the energy. We need the jobs. We have environmental concerns that need to be addressed. And generally speaking, the community doesn't have the technical expertise to really understand a great amount of the details that are important. We have the engineering and science community, which we may not be oil and gas developers, but we know a lot about water management. We know a lot about environmental management. So we're bringing our skills to the table to help accomplish this. And then you have the regulators. Regulators faced with a huge increase in demand as a result of this development activity, having to respond to that. They have responsibility to respond to that. It's a new challenge, and they have stretched resources. So all of these factors come together and represent the challenge that we have as a society, and that is to access our energy resources and do so in an environmentally sound way. So this concludes my introductory statement, and I will turn it over now to Kevin Rice.
Thank you, Hunter. I appreciate it. Thanks for all for joining us today. My name is Kevin Rice. As mentioned earlier, I work for Baker Hughes, one of the major oil field service companies involved in the drilling process, the completion of well process, as well as hydraulic fracturing. What I'm going to talk you through today is a bit of an overall understanding of how we technically drill and complete a well and go through the fracturing process as well. One of the things that you'll see on the slide in front of you now is a picture. Several of our descriptions as we go through the slides, you'll see quite a bit of detail in diagrams. And one of the things I want to point out to you in every diagram that you see here is the lack of scale. It's very hard to judge scale in these diagrams. The drilling rig you see here, depicted as an actual picture, is about 150 feet tall. The wells that we speak about in this area here are in the neighborhood of 10,000 feet deep. So you're talking 10,000 feet from here to here versus a scale of 150 feet here. And when you're actually talking about the width of a well, when you're talking about the diameter of the casing, this is 24 inches. So you're talking 2 feet across here, 150 feet tall for the rig, and 10,000 feet is a common depth for these wells. So just a comment on scale before we get into some of the further diagrams that really can get confusing if you're off base with that scale. So what I'll talk to you about today is the drilling process, the completion process, including how we cement a well, and also how we perforate a well so that we can allow the hydrocarbons to flow. And then I'll go through the hydraulic fracturing process in conventional wells that have been around, as Hunter mentioned, since the 1940s and a very well-established practice since the 50s at least, and cover a touch on horizontal drilling, which is one of the enabling technologies that has allowed shale to really come into play, and tell you really what the differences are between conventional and unconventional. If we move on into the drilling process, there are wells drilled in the United States today that go up to 35,000 feet in depth, and that's just straight vertical depth. When you look at the typical wells that we do in shale reservoirs, oftentimes they can be 10,000 feet deep, but they can also have a lateral horizontal section that's 10,000 feet out. So when you're trying to reach that from surface, you're actually going 20,000 feet, although it's 10,000 down and 10,000 out. There are almost 65,000 new wells drilled in the U.S. in 2011, and that was done with basically 1,900 rigs. If you do a little math on that, you see that a typical well, an average well in U.S. land, takes anywhere between a week and a half to 2 weeks to drill. It's a relatively quick process, actually, when you consider the depths we're going. The U.S.-based rig count right now for this past month in August was 1,914 active rigs working. And if you look at the breakdown, we had roughly 25% of those drilling directly for gas reservoirs and 75% drilling for oil reservoirs. And the reason why I mention that, if you look back at statistics from a year ago, those numbers were basically the opposite. Everybody was drilling for gas. But because we have had significant success in bringing gas to market in the United States, the price of gas has fallen drastically. And Hunter touched on those numbers and the differences between the price of a barrel of oil and the price of a barrel of oil equivalent of gas. And basically, right now, the driver for most companies is to try and produce oil as it is more lucrative. Most of the companies that we speak about are not privately held, and they're not done just for the greater gain of the world, but they're done for absolute profit. So oil is more profitable to go for at the moment, and you see that very quickly in the numbers. If you move to the next slide, we'll see how do we actually get to the oil and gas? What does the drilling process look like? Again, I point out the rig here is the small thing at the top. We have a drilling rig, which actually, much like if you have an electric power drill in your house, right? The whole purpose is to provide a rotational torque and actually drill a hole. It controls the downward force of the bit. When we're actually talking about getting to these depths, the rig controls the weight of the full string that goes into the hole. When you are talking about vertical drilling, it actually provides the rotation torque necessary to turn a full drill string and do the drilling process. Actually cut into the rock, cut into the ground in the formation that's there, and actually deliver that back to surface. And when I say deliver that back to surface, obviously when you make a hole in the ground, you create cuttings that have to be removed from the hole. That is done by a process of circulating drilling mud, which is a fluid that we'll talk about in detail in a few minutes. So when we get to the point of talking horizontal drilling, there are several techniques that have come into play that really have enabled us to exercise our ability to get at these shale wells. One of those is measurement while drilling. So during this drilling process, we actually have tools in the hole that allow us to tell exactly how deep we've drilled, exactly what the inclination is from vertical, so whether or not we're drilling a straight up and down hole or whether we've turned it, and to tell us an azimuth as well, so we know which compass direction we're actually drilling towards at any point in time. So these wells are planned in advance, one, to make sure we don't intersect any zones we're trying to avoid, make sure we don't intersect any wells that are already drilled in the area, and make sure we actually get to the target zone and get to what we're trying to produce. How we know where the target zones are is by using logging while drilling, as well as seismic data that we've collected beforehand. But logging while drilling enables us to actually look at the formations as we drill and get real-time information, reporting back exactly where is the bit and what's it seeing. So we can tell mineral composition, we can tell porosity and permeability, hydrocarbon saturation, some basic geological characterizations. All that can be done real-time while we have the tools in the hole. And one of the things that allows us to actually drill horizontally is a downhole drill motor. And what I like to use as an analogy for that is many of us are familiar, at least in general terms, with the massive tools that were used to build the channel between under the sea between France and England. And basically, if you imagine that, it actually pulls itself along as it builds a hole through the ground. And a downhole drilling motor is much the same thing. It's attached back to the surface by the length of drill pipe that's actually in the hole, but by circulating fluid through a series of fluted centralizers, you actually provide torque down at the end of the bit, and it's not as complicated as maybe I've made it sound, but it actually enables us to drill horizontally without just pushing in from the surface. What you'll see in the picture to the right is the final example I want to bring to you for this logging while drilling. One of the things we're able to do now is actually look at image logs. This is taken by one of the Star Trek tools provided by Baker Hughes, but basically it enables you to see the actual fractures that are in the rock as you drill. So there are natural fractures in our shales and natural fractures in our existing formations that we go for production. And being able to see exactly what those look like before we get to the final zone allows us to plan the way we do our completions and ensure that we're actually producing hydrocarbons, not producing excess water that Hunter mentioned we'd have to wastewater dispose after the fact. So it's quite an enabling technology to make sure that we're producing the right thing. I previously mentioned MUDs, drilling fluids. Basically, these are circulated down the drill stem and back up the outside, the annulus. And they basically create a jet down at the bit that it helps cut into the formation. And they remove the cuttings from the ground that you've actually dug up with your bit. And they also serve to lubricate the bit and kind of control the stability of the borehole. If you think about it, if you just go out in your backyard and you start digging a hole, you can only get so deep before it starts to cave in on you. One of the major functions of drilling fluid is to create a hydrostatic head and a pressure that enables you to have some borehole stability. These muds are recirculated and they're used over and over again, so it's not like they flow out of the well and they're disposed of. They're actually they're created with barite and some other natural chemicals in most scenarios, and they're used over and over again. We also go into a lengthy discussion of cementing, and Hunter touched on the fact that surface and groundwater are some of the areas where we absolutely must make sure that we're protecting the environment. Cement is one of the main low-tech tools that we use to do that, and it provides a permanent bond between the casing that we put in the ground and the formation. We'll talk that on the next slide. I'll show you some pictures of exactly what I mean between casing and formation. And it provides some stability and isolates between the zones. Cement is actually pumped directly from the surface. It goes down the inside of the pipe and back up the outside. So you get it into the position where it can isolate the actual formations from the surface. If we look next at there are quite a few tools that we use. This stuff is not just sackcrete. You know, it's not the kind of stuff you would go down to Home Depot and buy and mix up and pump down an oil well. It's very well engineered. There are a lot of quality controls that are done prior to placing the cement, during the placement process, as well as after placement, to ensure that we're actually creating the right type of integrity that we expect. If you look at the cementing stages, I'll spend a little time on this slide just to try and give you a better idea of exactly how a well is drilled. The first group of pipe that we put in the ground is conductor pipe, and it's often 24 inches in diameter, as I mentioned earlier. And it's hammered into the ground in most cases like you would see piles that are driven at a construction site. So imagine you've got a 24-inch piece of pipe, and it's probably between 50 and 100 feet long, and you beat it into the ground. And as you beat it into the ground, obviously it's full of dirt in the center, and it has a bit of stability. The biggest reason we do that is to kind of create a stable work platform for us to start drilling this well and isolate any shallow groundwater that might exist within the top 50 to 100 feet. Once we get it in place, we drill out the inside with a drill bit and the rig over the top, and actually pump cement in place. And the cement you can actually see here is the gray area. So this 24-inch piece of pipe will drive into 50 feet, and then we'll pump cement around it so that it's fully sealed to the surrounding formation. Next we come in, we drill it out and drill deeper. We drill to a depth of about 500 feet, and we run a next smaller size of casing inside. So this is metal steel pipe, just a steel tube, and we run that down on the 20-inch size inside the 24-inch to a depth of somewhere around 5,000 feet. This is the main barrier against groundwater aquifers. In the Marcellus, which Hunter mentioned is the northeast part of the country, this pipe can go to somewhere around 500 feet, and that we cement it in place as well. So that's the gray you see here. Again, providing the bond between the formation and the actual pipe. And we drill out again. We drill with the next smaller bit size, and we provide the next smaller set of 13 and 3/8 inch typically diameter pipe to go in the ground. And this can go anywhere down to 16,000 feet. And it isolates the different formations, but it also, there's a finite amount of depth you can go before you have to put a piece of casing in, otherwise the hole will collapse. So you have to continue to get smaller as you go further down. And finally, we put our production casing in place. And the production casing is often 5.5 inch in the shale wells that we're developing now. And it can go down, as I said, to 20,000 feet or even deeper. It isolates the production zone, which is this zone down here, from all the other formations. And this will be the actual string that contains all of the pressure and fluid necessary to hydraulically fracture the well. And it will be the string that actually has the flow of hydrocarbons flowing back up when we eventually put it on production. Now, if we return to the next scenario of, okay, we've put in this string of metal pipe into the ground. We've got it to our hydrocarbon producing zone. We've fully cemented it in place so that it's completely sealed and nothing can get in or out. And now we want to turn it into something that can produce oil and gas. The way we have to do that is we actually have to poke holes in our perfectly pristine environment that we've just created. And we do that in a couple of different ways. One way we do that is actually by explosive perforating. So we run in a charge of just shaped charges like you would see in demolition for buildings or other deconstruction projects. And these are very specifically tailored to the industry. So this is something that blows holes directly through the pipe. Once we get that in place, it allows the hydrocarbons to flow in. Another approach that we can use is the use of multi-stage fracturing systems, where we're actually, as you can see here, we put a set of sleeves that have ports already in them before they're installed, so that they you don't have to blow a hole in your perfectly pristine pipe. So that's the completion tool scenario. Once we get our completion in place, we need to actually get to the point of hydraulically fracturing. And in conventional oil and gas wells, this was done not so much to force a well to produce, but to actually create a better producing well than one that was not fractured. So you're basically pumping fluid into the wellbore to create cracks. And the more you pump, the greater the width or length of the crack will be created. And then you pump sand along with this fluid so that the crack is held open while the production takes place. As Hunter mentioned, a lot of the fluid flows back out of that fracture once you get it in place. So you have to have a very engineered fluid to make all of this happen. And when we get to talk about why do we actually fracture conventional wells, if you think about a well bore and radial flow, all the flows converging, and it's very difficult to produce because of a converging effect where actually it chokes back the flow. When you fracture a well, it creates a linear flow path, so there's no convergence. And back in the 60s, there were some pretty interesting experiments done to try and quantify what does that actually mean when you fracture a well. McGuire and Sikora did simulations with electrical resistance that showed that the further you actually go out with a fracture to lower the resistance, the more production you'll get over time, basically. So length and width of the fracture were the problems, or were the saving graces rather of how you increase your production of a well. I mentioned proppants before, and this is basically sand in most cases, but it also can be ceramic beads. And the function of these are we create a fracture with a certain width, but as soon as we release the pressure, the fracture tries to close back on itself and seal itself back off. So we put sand in place to enable the actual oil and gas to flow back out of the fracture. So that's the basics there. And from a fracture mechanics standpoint, you the first thing that you do in fracturing a well is you pressure up to the point where you actually exceed the breakdown pressure and start to create a crack. The crack starts out circular, but basically the height is the same as the width, or length rather, and then it starts to spread, and the direction it spread is based on formation stress. And fractures actually, they grow always perpendicular to the dominant stress zone that you're seeing in the rocks. And one of the things that you kind of might need to think about there is if you're shallow in the wellbore, if you're at 2,000 feet, say, the typical dominant stress is overburden. It's just the weight of the rock above you. But as you get deeper, overburden is definitely the dominant stress, and so you create a different fracture mode depending on the depth you are in the well. If you look at fracture growth, actually we can fairly well tell what the shape will look like of a fracture before we ever make it. I mentioned the logging while drilling tools that we have to give us some data from the well. One of the things it gives us is this stress environment. So we actually know that, okay, this is a zone, as Hunter mentioned, that is a seal rock. So when we create a fracture here, we know it'll only grow basically to this height before it runs into a higher stress zone of rock, and the easiest way for it to grow is out instead of up. So this is something we use to actually predict where the fractures go. I mentioned before that the fluid properties involved with hydraulic fracturing are used to actually create a low pump pressure, pump friction rather, so that you don't have as much hydraulic horsepower at surface. We need to create fracture width with low to high viscosity fluids and transport the proppant in place. But after the proppant's in place, we have to have a fluid that actually returns back to more or less like a water, so that it doesn't wash the proppant back out of the well in terms of fluid engineering. So we've talked mostly about conventional wells now, and I'll move into the unconventional just as I get to my closing. Unconventional is where we deem the shale and tight gas. In conventional wells, you can think of the formation basically as a sandstone, and maybe you've got a sandstone coaster, and you know that the permeability and the porosity of it is such that it soaks up water pretty easily, and it would also let go of any fluid pretty easily as well. In conventional wells, we would fracture into that simply to increase the production, and it's just a stimulation technique. It's not a requirement. In tight gas wells, you can think of that, the formation is almost like brick or concrete. So there's not a whole lot of fluid that's going to be flowing in or out. It's very difficult to flow. And the unconventional is closer to granite and shale. And you absolutely have to have fracturing in order for it to flow at all. As Hunter mentioned, this is the source rock, and it just doesn't contain the type of volume in porosity or the type of permeability that allows the hydrocarbons to flow. If you look at shale, what is it? Hunter showed an outcropping as well. I mean, it's mudstone, siltstone, shalestone. It's the source rock, and it's got a very fine grain size, extremely low permeability. The natural gas in the oil actually, it sits within the natural fractures that are in the shale, and it's absorbed on the surface. It's not like a big pool to actually tap into. So that changes the whole method we talked about of just creating a bigger crack. What you actually have to create in unconventional wells is a fracture network. And so that's why you get multiple wells, multiple stages. As you can see here, these are some visualizations to show you what we're trying to create down hole to actually get stimulated reservoir volume. As we get further into this, you see that operators are upping their number of stages, upping the number of fractures, and getting their wells closer and closer together. Since 2006, there's been basically a doubling of fracturing stages every 18 months. So when we originally started, wells averaged basically 8 stages per well, and then last year they'd gotten up to 16 plus, and now we're currently doing wells with up to 40 stages of fracturing in each. So the returns on that are just such that it makes sense for the operator to stimulate more volume with a less number of wells. So in summary, hydraulic fracturing is absolutely necessary to develop the shale gas resources that we have, but it's not a standalone process. The key developments that are required to successfully produce from shales are measuring while drilling, logging while drilling, downhole drilling motors, the multi-stage completion tools, and also ways of projecting fracture networks. I'll now turn the call over to Tom Tomastik with Ohio DNR to speak about the risks and benefits of hydraulic fracturing. Thank you.
Thanks, Kevin. What I'm going to talk about a little bit is the risks, the benefits, myths, and the realities of hydraulic fracturing. I'm going to cover a little bit of general oil areas, and then I'll get into a little bit more specific details in regards to Ohio's regulatory framework and how we address hydraulic fracturing. Hydraulic fracturing is not something new. It has been basically around, I think Hunter had said, since the 1940s. There's kind of an argument, I think, between Kansas and Oklahoma who had the first hydraulic frac job. Kansas saying 1946, Oklahoma 1949. It's pretty much a routine technology, as both Hunter and Kevin has explained, for over 60 years. We have over 1 million oil and gas wells in the United States that have been hydraulically fractured. Most oil and gas producing states have regulations that address hydraulic fracturing. The disposal of the fluids from the frac job are regulated under the Safe Drinking Water Act. A number of states, such as Texas, Oklahoma, Colorado, and Ohio, have recently passed new regulations addressing chemical disclosures associated with the chemicals used in the hydraulic fracturing process. A website that is been developed to view chemical disclosure, currently in counting over 27,000 wells, can be accessed at www.fracfocus.org, and that was designed by the Groundwater Protection Council. Just touch briefly on the U.S. EPA study on hydraulic fracturing. At the request of Congress, U.S. EPA was challenged to conduct a study to better understand any potential impacts from hydraulic fracturing. Researching is covering the full lifespan of the water from usage through the hydraulic fracturing stage through ultimate disposal. The first report, progress report, is planned to be released actually here within the next couple months, and then a final draft report by U.S. EPA will be released in 2014. And now I'm going to briefly just touch into some of the aspects of Ohio's oil and gas development and hydraulic fracturing. Ohio has been an oil and gas producing state since 1860. Most of the oil and gas wells in Ohio have required some type of stimulation to make them economically viable. As Kevin was showing on some of the slides, a lot of our formations are what they consider tight formations that require some type of stimulation. Some of the first stimulation actually started in the 1880s in what we call the Trenton limestone and the Finley oil field area, which you can see in the upper left-hand part of the state. Initial well stimulation techniques in Ohio. Most wells historically in those days were stimulated by explosives using nitroglycerin. That's what they called shooting the well. Typically, we would see 1 quart of nitroglycerin used for every foot of the reservoir rock to stimulate it. This was the primary completion technique employed in Ohio and in many other states until the advent of hydraulic fracturing. Hydraulic fracturing in Ohio was first used in the East Canton field in 1951, and met with considerable success, particularly in the tight Clinton Sandstone Formation, and hydraulic fracturing since that time dramatically reduced the number of dry holes being drilled for oil and gas in Ohio. Tens of thousands of oil and gas wells have been successfully hydraulically fractured in Ohio since 1951, and we currently have about 64,000 producing oil and gas wells in Ohio, and about 95% of those were stimulated by hydraulic fracturing. There's obviously a lot of misinformation being put out in there regarding hydraulic fracturing. One of the things that we did in a study here in Ohio is we conducted over 1,000 oil and gas investigations since 1983, and we went back through those investigations, and there were no cases of where hydraulic fracturing had caused groundwater contamination. This is a diagram I think that Kevin had shown, and what it is showing there was a report done by both Halliburton and American Oil and Gas reporter regarding the extension of the hydraulic fracturing from, this is from the Marcellus Shale. As you can see below the lines with the heights of the hydraulic fracturing compared to the blocks of blue up in the top of the page, which indicates the depth of the fresh groundwater aquifers. So you have thousands of feet separation between the actual top hydraulic fracture and the drinking water that people are using every day. One of the things that I do want to explain that a lot of people don't understand is you really scientifically cannot hydraulically fracture back to the surface from the oil and gas producing zone. What happens is at depth, as Kevin demonstrated, you create a vertical fracture, but if that fracture extended and continued upwards well beyond your zone and was approaching close to where the freshwater aquifers are, at a depth of about 1,000 to 1,200 feet, that fracture would obviously start turning and going sideways. What happens at those shallow depths of 1,000 to 1,200 feet is you're physically able to lift the overburden of rock. So consequently, your fracture would go horizontal and would not continue to move vertically up into the groundwater and cause contamination. Now, the potential contamination avenues for a hydraulic fracturing job would be through improperly plugged old oil and gas wells that could possibly be intercepted during a hydraulic fracturing treatment. But what we've seen in Ohio, and I believe it'll be the same in most of the other oil and gas producing states, is the potential avenues for groundwater contamination is your number one contamination source is going to be surface contamination. Spills, equipment failure, pit leakage is obviously a big avenue for potential contamination. Bad cement jobs is also a possible way to have groundwater contamination or contamination from fugitive or stray natural gas. Poor and improper well construction, casing integrity issues, and then improperly plugged or abandoned wells can also be a potential avenue for groundwater contamination. Regulatory reform has really helped, and I think if you examine most of the states, the oil-producing states, we have continued to pass new regulations through the years that have dramatically reduced the actual number of oil and gas contamination cases related to oil and gas activities. This is just a graph showing Ohio's study that we did of the over the 1,000 groundwater investigations that we conducted, and what it shows as we've passed new key regulatory reforms, we have continued to reduce actual contamination cases related to oil and gas operations. So that is one of the key things I think you continue to see in most of the oil and gas producing states is continued passages of new regulatory reforms to continue to dramatically reduce actual groundwater contamination cases related to oil and gas operations. Here's just a generalized schematic of a current Utica Shale well being drilled in Ohio. As Kevin kind of touched on with some of his diagrams, you can see how the well is constructed, typically with at least 4 layers of steel casing protection with cement. The groundwater obviously being isolated through what we call the surface casing. And in Ohio and most states, we protect what's called the underground deepest underground source of drinking water, the USDW. And most states like Ohio protects down to 10,000 milligrams per liter total dissolved solids. So we are protecting the groundwater well below what's currently used for human consumption, because one day that brackish fluid may be needed for human use. Here again is just a small cartoon. Obviously, Kevin touched on this a lot more than I did in any detail of a hydraulic fracturing job. And you can see again how the well is stimulated and how the fractures are completed. One thing I did want to touch on that these are the hydraulic fracturing and horizontal drilling are a merger of 2 existing technologies. As you saw, that hydraulic fracturing has been ongoing for well over 60 years. Horizontal drilling has been used fairly widely in the United States for the last 20 to 25 years. So it's not something really new. It's a merger of 2 existing technologies that has created this opportunity for the development of these unconventional shale resources. The chemicals used in hydraulic fracturing, we use acids, we use friction reducers, scale inhibitors, surfactants, biocides, clay stabilizers, breakers, cross-link, or dissolve. And basically all this is to help with the process. The acids help dissolve the minerals. The friction reducers minimize the friction as you're pumping the fluids away. The scale inhibitors prevent the development of scale deposits. Surfactants, which are normally in shampoos, help increase the viscosity of the fluid. The bactericides obviously kill any bacteria that may be harmful in preventing flow of oil and gas in the well. Clay stabilizers prevent swelling of the clays. And the breaker and the cross-linker also help with these types of fracturing jobs. Here's just an example of a real-life hydraulic fracturing job that was performed in Jefferson County, Ohio, back last December. As you can see, the vast majority, over 98% of a hydraulic fracturing job is predominantly water and sand. And the remaining chemicals make up, obviously less than about 1 to 2% of a hydraulic frac job. So obviously you're looking at maybe a 6 to 8 million gallon hydraulic fracturing job. 98% of that fluid or more is water and sand. There's a group called Stronger that does reviews in state oil and gas programs, and they conducted a review of Ohio's hydraulic fracturing program in January of 2011, and that report was released and available on our website. One of the summary of that report, which includes 8 industry, regulatory, and environmental officials that make up that committee. Basically, they reviewed Ohio's program, saying it's overall is well managed, professional, and is meeting the objectives. Just briefly on some of the conclusions, as I said earlier, we've never had a groundwater contamination case in Ohio caused by hydraulic fracturing. We continue to see changes in regulations that have dramatically actually reduced the actual number of groundwater contamination cases caused by oil and gas activities in the United States. New rules are in place in Ohio and in many other states that deal with more stringent well construction and cementing practices. And as I showed you earlier, we're seeing new laws passed to address chemical disclosure, pre-drill water sampling. One thing of issue recently at a conference I was just at, Chesapeake Energy in sampling of their pre-drilling water sampling program has sampled over 31,000 water wells so far, and interesting to find that over 25% of the water wells that they sampled in various states in part of this shale development, over 25% of those water wells had natural gas prior to the oil and gas well being drilled at the site. So what we are seeing is there are a lot of sources of methane that can be naturally occurring, that can be coming from other sources such as coal mines, coal beds, can be biogenic sources from and natural sources of methane from non-commercial oil and gas zones, and then also from legacy oil and gas problems as we've developed oil and gas in the United States since 1859. And now I'm going to turn it over to Bill Ritter.
Good afternoon, everybody. At least it's afternoon in Colorado, and it's a real honor to be part of this webinar and to be with Hunter and Kevin and Tom. I really appreciate the fact that there's so much subject matter expertise that's part of this webinar. I've been asked to just talk about the economic and societal benefits and barriers that surround natural gas, and I think we've actually heard really good summaries from the other three presenters about many of the technological innovations that have made the exploration of unconventional shale gas possible, and we've also had some discussion about those barriers. But I want to tell you a little bit about sort of the Colorado experience and what we've seen happening around the country, and really give you that as the context for how we move forward with environmentally sound production of natural gas. When I became governor in 2007, we look back to 1999 and we had 1,000 permits for natural gas drilling that were granted. And the year before I became governor, there were 7,000. So in a 7-year period, there was a 7-fold increase in the number of permits, and this had everything to do with shale gas being discovered in different basins in Colorado and the use of both hydraulic fracturing and directional drilling. But what we also understood was that our rules that we had had really in place for 30 years had not kept pace with the technical and technological innovations that had happened over that same time frame. So even as I campaigned for governor, I had a lot of citizens in Colorado that were complaining about the lack of adequate regulations where both air emissions and where water was concerned. After becoming governor, we reconstituted our Oil and Gas Conservation Commission, and then we went through about a 1.5-year long process of totally rewriting our oil and gas rules and really modernized them in a way that took into account all these technical innovations and the technological innovations and this big upsurge in drilling that had happened as a result of it. So since that time frame, there's actually been some additional things that have been done, and I would hold out Colorado's rules as a pretty good set of rules, actually, as states go, a pretty good set of rules that really provide for sound regulation. I'm now at Colorado State University running a center called the Center for the New Energy Economy, and part of that is I work with states around the country on energy issues, and among those issues, I've done some work on regulation of natural gas production. One of the things that we at Colorado State University say is that we believe natural gas can and should be part of a clean energy economy going forward, not only in America but around the globe, but that in order to do that, strict regulations, just as a matter of public policy, strict environmental regulations have to be part of our future for natural gas production. We have, like I say, we've seen states around the country put in some really significant regulations, and Tom alluded to Ohio's regulations. If you look at Senate Bill 315 that was passed this past year, it is a great example of a state who kind of in the nascent stages of oil and gas production saying we want to do this right, we want to put these in place, and And they're pretty good. They're a pretty good set of regulations. There are other states in the West, Wyoming, Texas, gas, extraction producing states. These are states that have done a fair amount of work on making sure there are a good set of regulations. So if that's the case, then why is there still a debate? Why are there states like New York and New Jersey where there are moratoriums, California where they're debating a moratorium, or even in Colorado that has this great set of regulations? Why are there local communities that have either passed a moratorium in their locality or in fact have considered a moratorium and maybe rejected it, but in close votes in some cases? The answer is we think that while we've talked a lot about the technological issues and some of those, the answers to technological issues and the kinds of strict policy regulations that can be put in place as a part of looking at those issues, the industry still, in many places, hasn't convinced the public, really, that it should have what I call a social license to operate. So let's examine what some of the barriers have been to the industry really doing what it can to convince the public about this social license to operate. It's been alluded to before, but let's just go back to the air emissions question. There are a couple different parts to the air emissions question. One of those is methane leakage. So at the wellhead, the fact that there is methane leakage is something that most people agree about. The question is, how much methane leakage is there? There have been a couple of studies. A study from Duke, a study from Cornell, the National Oceanic and Atmospheric Agency have had some studies, and they looked at different levels. And the industry disputes the sort of numbers that have been set forth in different studies, but the fact of the matter is, it is presently a matter for debate how much methane leakage. Yes, well, why is methane leakage so important? One of the reasons gas is this important commodity for us to use is because there are a variety of values in burning gas vis-a-vis other fossil fuels. If you compare gas to conventional coal-fired furnaces, you can reduce the NOx and the SOx pollution by 70 to 80%. You reduce the carbon by 50%. You eliminate the mercury virtually in burning gas instead of coal. And so people say, well, gas is a much better fossil fuel. Problem is, if the methane leakage is actually as much as some of the studies have said, then there's less of a climate benefit, perhaps no climate benefit to burning gas because of the life cycle analyses that are done. For our part, we think that what we need to do is study methane leakage and study it around the country at a variety of places and really look at it in places where adequate rules have been put in place that involve well completion. Colorado is one of those places. But, if in fact a producer is not concerned about methane leakage, not doing what they're supposed to according to the rules, then there may not be any climate benefit to natural gas. And this is why it's so important to encourage responsible production. The other air emissions question has to do not just with methane and methane leakage, but has to do with actual emissions from drilling itself. A place called Pinedale, Wyoming was put under a non-attainment order by the Environmental Protection Agency, not because of the methane, but because of just the emissions that were coming from the drilling equipment. So it's another issue that companies really have to understand is in fact an air emissions issue and that they have to deal with. Back to methane leakage, the other thing that you have to look at in the life cycle analysis is not about just the wellhead production, but what's called midstream, the pipes, the valves, and the tanks. And if there's methane leakage along that, then again that adds to sort of the detriment of the life cycle analysis to natural gas. And again, we think these are solvable problems. I'm a big fan of natural gas being a part of our future for a clean energy economy, but air emissions is this issue that the industry has to, I think, constantly look at and just improve upon all the ways they can to trap methane and to reduce their own emissions when they're drilling. Secondly, as it relates to water, again, this has been alluded to before, but Colorado happened to have had a pretty bad drought summer this past summer, and because of that, our rivers were at fairly low levels. And at the same time, we've got counties in Colorado that have the most drilling rigs of any county in America, Weld County. So we're doing a lot of hydraulic fracturing, and that's water consumptive. And so in arid places, particularly where there's a competition perhaps between industrial users or farmers or even municipal users with energy producers who are hydraulic fracturing, and paying attention to water availability is really part of the set of issues that the industry has to confront. The industry is doing a variety of things to try and reduce the water that they use in hydraulic fracturing. There's even R&D happening that looks at waterless hydraulic, or not, it wouldn't be hydraulic, waterless fracturing techniques. And those are really important advancements that we see taking place on the R&D front that we hope may someday replace hydraulic fracturing altogether, so water is not the issue. It's been alluded to as well that there are water treatment issues, both with the fracking fluid and with the processed water that also flows up the wellhead. And how you treat those can really be, it can vary from state to state to state depending upon the state rules. Deep well injection is a part of how some states allow the treatment or the disposal of water that comes back up out of the well. And with deep well injection, it's important as well that the operators understand the kinds of issues that they can create if they inject water in deep places, in the wrong places. There's a concern among some in the community about seismic activity that might be created from deep well injections in fault lines or in the sort of geological fault lines, and so it can create a problem. So there's the water issue, there's the methane issue, but there are sets of rules that have really looked at these and have, I would suggest, have really addressed these in a serious way. Ohio's one, Colorado. The International Energy Agency has published the 21 golden rules that they believe are necessary for the most environmentally sound types of hydraulic fracturing that can happen around the world, in the United States and around the world. It lists 9 of those rules. It lists Colorado as having sort of the best practice in place. The EPA actually has 4 rules where it has the best practice in place. So we've done all this to try and address both the air emissions issues and the water issues from the rules that we have in place. But the fact of the matter is there's still great concern, and part of that is just that I think industry for such a long time would not disclose the fracking fluid, the kinds of chemicals that they were putting in fracking fluids, and they really lost the public relations battle over that. The industry came around in the last couple of years to being willing to disclose or to agree to rules that required them to disclose, with some exceptions for what they still call trade secrets, though they're very narrow exceptions. I actually congratulate the industry for doing that. But in the meantime, they really sort of lost the public relations battle, and I think that has everything to do with what's happening in so many communities and in states where there are these moratoriums or where moratoriums are being considered. The other part of the social license to operate is for the industry to understand that this is a pretty intensive industrial process. The process of drilling for gas, drilling for oil, hydraulic fracturing, they're pretty intense. They involve, like we said, these air and water issues, but there's also a variety of nuisance activities that can be a part of it. Dust from roads, constant truck traffic, the noise from the drilling operation itself. Those are all things that they need to take into consideration. So in Colorado right now, our Oil and Gas Conservation Commission is considering a whole new set of rules that involve setbacks or setback requirements. And it's helpful for the industry as well to participate in drawing up those setback requirements and understanding that in really obtaining their social license to operate, what they want to do is go after this very important resource and go after this resource in a way that still helps suburban communities, urban communities in close proximity enjoy their quality of life in spite of the drilling activity that's happening. So what we have to do, what we believe is necessary here, is for the industry to work with the environmental community and for people who are in the academic world, who are involved in research and development, to work as well there, really ask the question, how do we ensure that everything we do with oil and gas production is done in a way where it's the most environmentally sound practice in place, does our level best to protect air, to protect water, to protect communities, and quite frankly as well, in any places in the West, to protect wildlife. In our set of rules in Colorado, we actually have special wildlife provisions that require companies to file comprehensive drilling permits so that we can be assured of protecting wildlife habitat, but also wildlife migration patterns. And that's important for the industry as well as the environmental communities to work together on. That we really need to do this, and we need to do it here in the United States, in part because we enjoy a leadership role in the production of tight shale. I'm the co-director of a policy institute in Shanghai, China. China has vast tight shale resources that are still pretty much undeveloped, but the development is really at its first stages. And we think that we in the United States should really be part of helping the rest of the world understand how to produce gas in an environmentally sound way if it's going to be this important resource. So let's assume then that we do that we actually look at natural gas and say, when we produce it, we're going to do all that we can to protect air, to hold down water, hold down air emissions issues, to trap methane and utilize it as a natural gas as opposed to letting it escape into the air, to do all we need on the water treatment side, the recycling side. Then natural gas can be a part of a clean energy future. It's not only cleaner burning than other fossil fuels, but it also integrates with renewables. In Colorado, we have a 30% renewable energy standard, and quite frankly, out of all the different ways to firm that, to firm those renewables, wind or solar, the single best way that's sort of available to us at scale right now is natural gas. And so natural gas and renewables working together can be part of a clean energy future for states and for the nation. And again, we can demonstrate this leadership role. So from my perspective, it's important for us to view all these issues that have been discussed today as issues that we need to continue to address. And as the technology develops, make sure that we have strict regulations that still protect our air, protect our water, protect our wildlife, look at land use issues, look at all the kinds of things that can be environmental impacts from this intensive industrial process, but to also understand that the benefits to this are about the environment for sure. There are also economic benefits, and as Hunter described in his slides at the beginning of this, there are national security benefits to this by us becoming close to energy independent, and if not energy independent, at least energy secure. That's kind of the way we should think about natural gas, but we're not going to get there unless we really can come to a consensus in this country about how the industry gets to a place of having the social license to operate and really convincing people who are both policymakers and folks from the environmental community that it's possible for natural gas to be part of our clean energy future. Again, thanks a lot for letting me be part of this, and I think I turn it back over to Hunter, who's going to transition us into a question and answer period.
Well, thank you very much, Governor Ritter. That was fascinating. All right, we have received a number of questions from the audience, and we do want to encourage additional questions. David, did you want to provide any further instructions on how folks can do that?
Yes, just real quickly, if you do have a question or a comment for our panel, just click on that general chat tab near the bottom of your screen and then type your question in the lower box that appears, and then please be sure to press enter or just click the send button to submit your question. And with that, Hunter, I'll turn it back to you to address some of the questions that were submitted earlier.
Okay, very good. Well, Governor Ritter, there's a question here that I think maybe you could take a crack at, and that is, how do existing regulations here in the United States on fracturing compare to standards that are being developed in other countries?
Well, that really varies from country to country to country. There was a company in the Ukraine that's involved in extracting, and it actually follows Colorado rules because it knows it says in its brochure that the Ukrainian rules are actually inadequate for environmental protection. I think there's a variety of places in Europe, for instance, where they are very nervous about hydraulic fracturing because they're watching some of the studies and not understanding sort of the benefit of tight regulations and strict regulations. As I said, China's sort of at the earliest stages in this. I did visit Israel. Israel has big offshore gas, and they're trying to do this in an environmentally sound way. So you can look around the world, and really there's no place in the world that sort of moved farther along the trajectory in really regulating natural gas extraction, particularly hydraulic fracturing, than the United States.
Well, thank you, Governor. Tom Tomastik, here's a question that maybe should be addressed by you. If there is a groundwater source near a shale, can you conduct hydraulic fracturing near that site?
I can speak from Ohio, from our standpoint. we do allow development of oil and gas well drilling and hydraulic fracturing in close proximity to source water protection areas. What we do require, though, is very stringent additional conditions attached to those permits that, again, will alleviate a lot of the potential for groundwater contamination or surface spills. So we do address that by requiring additional conditions to a drilling permit if it's in a close proximity to a source water protection area.
Okay, Tom, there's another question that maybe you could address, and that question is regarding flowback fluid. How would you handle flowback fluid treatment or management if the characteristics of the additives are proprietary?
We pretty much handle all of the flowback by flowing, at least on the unconventional horizontal wells that have these large multi-stage hydraulic frac jobs, by flowing back into tanks, so that nothing in Ohio is on the unconventional shale wells is being put into drilling pits or anything like that. So we're in a closed loop system that we're dealing with. Our new regulations on Senate Bill 315 does require the chemical disclosure. If there was an event of a spill, we do have the ability to release proprietary data to medical personnel or emergency personnel if they need it.
Okay, very good. Hey, Kevin Rice, how is the number of stages of fracking related to production? And along those same lines, what is the typical life of a producing well?
Sure, and I guess I tried to touch on the number of stages, and I may have glossed over it a bit, but basically, when you get into a shale formation, you're trying to connect up the existing natural fractures. And if you fracture in one point during the well, at the very, very end of your lateral, you'll only touch a small amount of those natural fractures. So what you need to do is you need to touch it there, and then you move up with another stage, and you touch the natural fractures maybe 200 feet above that, and again 200 feet above that, and 200 feet all the way back out your lateral. And oftentimes this is just done geometrically. If you've got 10,000 feet of lateral, you divide that by the 20 stages you want to pump, and there you go. Every 500 feet you're going to have a stage of fracture. But what it does, it enables you to touch into more of the natural fractures where the existing gas or oil already sits, and it gives you more access, basically.
Okay, and Kevin, another question about drilling is, how does the pipe make the turn to a horizontal?
Sure. And you know, we look at it on the drawings, and again, scale is a concern. The actual turn that we're talking about making takes place over hundreds, if not thousands of feet. So we actually use a term called dogleg or dogleg severity. Just like you would think of doglegs if you're playing golf and a hole has a turn in it, we have a certain amount of angle that we allow over a period of 100 feet. And we typically don't allow that to be more than 3 to 5% of an angle change over that method. So, you know, this pipe, when you get it over thousands of feet, becomes quite flexible, and it does just turn. But you're not making an immediate 90-degree turn over a very short span.
Okay. And Kevin, I think you touched on this, but maybe just a quick reminder of the methods for testing the integrity of the completion and then the long-term integrity as the well operates.
Sure, absolutely. One of the things, especially with the cement and how we test it to ensure that it's created a bond, once we get the casing in place, the metal casing in place, and the cement around the outside, we actually apply a pressure test to that's recorded and very well managed to ensure that it's actually holding and it doesn't leak off any fluids or it's basically air and fluid tight. And we do that both in a positive manner where we're pushing pressure against it and a negative manner where we're pulling pressure from it to ensure that it's actually created quite a good seal. There are other methods that we can actually do using logging tools to verify the bond is correct. We have what's called a cement bond log, where you can actually look over a long period of the casing with a tool to ensure that it actually is well bonded and holding a seal.
Tomastik, here's another question for you. Can you provide a sense for the surface impacts associated with shale gas development? For example, in Pennsylvania, a typical well pad seems to be around 5 acres. When the formation is completely developed, how dense will the pads be? How significant is the surface impact?
I could speak a little bit both from a tour in Pennsylvania and then development here in Ohio. Typically what we're seeing is probably a 4 to 5 acre pad development, and again, that's to at full development of maybe 6 to 8 horizontal wells off that drilling pad. It dramatically reduces the surface in footprint that we would typically have if you were drilling conventional vertical wells, where you would have to have possibly 30 or 40 conventional vertical wells to be able to drain the oil and gas that you're now able to access through a 4 or 5 acre pad with 6 to 8 horizontal wells. A lot of these horizontal wells are actually being drilled out anywhere from 4 to 7 to 8,000 feet horizontally, so you're accessing an extensive amount of the reservoir horizontally. In Ohio, typically we see spacing-wise for individual horizontal wells probably in the range of 160 to 180 acres. So if I'm drilling 6 wells or so, off of a pad, I might be encompassing a 1 square mile area for that pad by itself. So typically the pad locations will be pretty much spaced a pretty good distance apart compared to what we would typically see with a conventional vertical well that would be more closely spaced and require more surface footprints than we would with a horizontal location.
Governor Ritter, there's a request for a little further explanation on regulations. And the way it's stated is, the governor mentioned the need for more research relative to fracking and environmental qualities. Can more comments be made on what research should be done and by whom?
Well, I think the number one thing is really about methane leakage, because there is some discrepancy between some of the academic studies that have been done and some studies that the industry itself has done. The Environmental Defense Fund is an environmental group that is really focused on this issue about getting gas right. They're not among the environmental groups that think there should be a moratorium, but they are among those that believe we need to make sure that we do everything in an environmentally sound way. So the Environmental Defense Fund is dedicated actually to putting some significant amount of dollars into their methane leakage studies. Actually, Colorado State University, where I am now, we believe will be involved with the Environmental Defense Fund in looking at the midstream, at what I mentioned before, the pipes and the valves and the tanks. But there are a variety of studies being done by different kinds of institutions of higher learning that look at methane leakage at the wellbore. And people typically agree that there is a place where if methane leakage is sort of below a certain amount, in the sort of 1 to 1.5%, even below 2%, it's got a real climate benefit. Natural gas does. But if it's up around 4 or 5% at the wellbore, then it's not going to have much of a climate benefit. And I think Kevin can probably speak to this, to the issue of sort of where the industry is on this. But that's one of the studies. One of the other studies, and this is more instead of research, is just more sort of developing the technology, and it really has to do with what a few of us talked about, and that's looking at sort of water treatment, water recycling in places where water availability is an issue, but water treatment and sort of what we do with that water when it comes back out of the ground. Those are all things that I think are going to be important for the natural gas industry to continue to work on, and for folks in higher ed and in the environmental community to work on them with.
Okay, the next question is, could you please explain the magnitude of water fluids produced via hydraulic fracturing? And I think I'd like to take a shot at that. I did show a slide early in my presentation about the magnitude of water use of shale drilling versus other uses. So, for example, in the Marcellus, when the Marcellus is expected to be drilled at a peak rate, which is about 3,000 wells per year, the anticipated water usage is about 30 million gallons of water per day. Now, that compares as a fairly small amount relative to mining, and which uses about 182 million gallons per day, and then public water systems, industrial, et cetera, which have much higher uses. But your point is really, your question is a very good one, because there are areas of the country that are under drought conditions, and any additional stress on water resources is a difficult stress. Governor Ritter mentioned that in Colorado. We have the same situation in South Texas. So there's a lot of innovation being applied in terms of minimizing water, utilizing low-quality water, recycle of water, and minimizing disposal of water into very deep zones where it can never be used again. This is an important matter in the overall development issue, and it will continue to be going forward. I'd like to offer any other speakers to also speak to that question if anyone has anything to add.
Okay, so, Hunter, this is Kevin. I guess to kind of close the loop on both Governor Ritter and your comments, the industry itself has just got a vast amount of R&D that is going into these exact questions, right? How do we make less disturbing chemicals to put down our wells? And we've gone to the food industry to get a lot of things now. One of the major things we pump is actually guar that creates viscosity. And pretty much every one of us this morning took out our toothpaste, squeezed it onto our toothbrush, and put guar in our mouth. And it's also in the ice cream. Basically, it's a bean. Right, so we turn further and further to existing things that we know do not affect the environment. So the R&D is definitely there, and the need to do it is clear. We've come just a dramatic way in the past 5 or 6 years. And to decrease the amount of water that we actually need, it's a similar thing. We found more and more ways to use the flowback water again to reuse and recycle. Instead of dispose, and that's again adjusting the actual chemical mix to take a higher volume of solids to be able to apply it during our frac treatment.
Thank you, Kevin. So here's a question about water treatment, and that it is: how is wastewater treated and disposed of? Deep well injection only? So it's a very good question. There's a lot of emphasis on recycle and reuse in the drilling and fracturing process. And for those purposes, the amount of treatment required is fairly low. There's a need to remove solids. There's a need to remove oil and grease to an extent. There's a need to treat for biological contamination, things of that nature, or risk of biological growth in the formation, things like that. But relatively simple treatment. Where it becomes complex and expensive is when treatment is required prior to discharge to the surface, in a stream or otherwise. And that's where higher forms of treatment and more expensive forms of treatment need to be applied. And depending on the conditions, depending on the source water, depending upon the discharge requirements, that can range from a variety of solids and oil and grease removal type technologies to salt removal technologies. And the real challenge is when you get to salt removal technologies, total dissolved solids, that it's difficult and it's expensive to remove salt from water. And that's where lots of economic decisions are made about whether it's cheaper to dispose of high salt water, a deep disposal well, or treat it for discharge. So very good question. It's a complex answer. It depends on the situation and the location and really the timing of when that treatment is needed. Governor Ritter, here's a question, and I think Tom Tomastik, you'll have some insights on this as well. Has the number of state employees responsible for enforcing regulations kept pace with the rapid pace of permits being issued?
So what I would say is, in places where they've tightened their regulations, typically they add enforcement personnel. But one of the complaints from some communities around the country, where communities think there may be adequate laws in places, that there's not adequate enforcement. And I've heard this from different communities in the Pennsylvania area, where they think the state actually done some work on improving its state laws, but still hasn't really, they still don't have the number of personnel necessary. I can't say whether that's true or not. I'm just telling you it's sort of a complaint that's come with it. There's the environmental community in Colorado would still complain and say that this is an issue that needs to be addressed. Even with the work we've done on our rules, they think that the well inspections are just not enough, that it should happen on a more regular basis. There should be, fewer wells as sort of the caseload for the well inspector. And I think this is, again, a place where states, in order to sort of get past the kinds of complaints that we've had to address, states are going to have to ensure that they have adequate enforcement.
Tom Tomastik, do you have anything to add to that, being a regulator in Ohio?
Sure. And what we've seen, and obviously we looked at developments in Pennsylvania and some of the problems that they faced with the rapid development. Ohio became very proactive in really staffing up to hiring a lot of additional employees. Probably within 2 years ago, we had about 35 full-time oil and gas employees at that point. We were still part of the Division of Mineral Resources Management, which was regulated oil and gas and the coal mining and industrial minerals mining in Ohio. We separated out as of October 1st of 2011, and since that time, we now have 110 full-time employees dedicated to oil and gas. We're looking probably to hire at least an additional 40 employees probably sometime next year. So we're in the process of being proactive to ramping up to be prepared to stay on top of this development of the Utica Shale play in Ohio. As we're still really in what we call the exploration stage. So at this point, we're trying to be very proactive to be ahead of the game.
Can I add something too, Hunter? This is Bill Ritter. A lot of states are looking at baseline monitoring as even a precursor to permitting, and maybe if not permitting, at least part of the permit, not a precursor, but as part of the permit. Look at it, baseline monitoring both of water and of air. And as we do that, that's going to require additional resources on the part of the states who aren't currently making that part of the practice. I think you'll see far more than what's gone on in the past in our future, so that they have something to compare to, whether it's the aquifer or whether it's air emissions, their air quality at the site of it, and that's just going to require more state resources as we go.
Okay, well, here's a question. I believe it's about NORM, naturally occurring radioactive materials. It's stated, how is TNORM, T-E-N-O-R-M,
yep,
liquid and drilling mud, best handled? And so Tom Tomastik, maybe you, and then Kevin Rice can.
Yeah, NORM is the naturally occurring radioactive material, which is exempt from federal regulations. TNORM is going to be naturally occurring radioactive material that is basically technologically enhanced, meaning that if I pump something into an oil and gas well that's non-radioactive and it becomes exposed to NORM, now it comes back as a waste and it is now radioactive, it's considered TNORM and has to be addressed in a far different manner than naturally occurring radioactive material. Ohio recently, through our Ohio Department of Health, Bureau of Radiation Protection, who has primacy of radiation requirements in Ohio, recently passed TNORM regulations in the spring of 2012. So again, we're being very proactive with this. We actually are now implementing with the Department of Health, Bureau of Radioactive Protection. We're doing some on-site sampling. Actually, my deputy chief is out today with them doing some sampling. We're going to be sampling well cuttings. We're going to be sampling drilling mud. We're going to be sampling produced water, flowback water, recycling water, in an effort to gain insight into what we are seeing in relation to norm and T-norm. If it's T-norm and it exceeds the state and federal requirements, then it has to go through proper disposal for that product.
Okay, well, I think we have time for about one more question here. And here's one related to surface impacts. I think, Tom, both you and Governor Ritter can speak to this well. Assuming that the existing road networks do not support the transport operations in rural regions, what are the efforts that are being planned to combat this issue?
I can speak both, from Pennsylvania and Ohio's perspective on that. Pennsylvania also was very proactive in that, and Ohio is now doing the same. What we're seeing is road maintenance agreements that are being developed. Most of these oil and gas major independent and major oil companies are very proactive in maintaining or repairing or even upgrading these road networks to well beyond what they were even before. We're seeing a large percentage of money coming in and upgrading these roads, both in Pennsylvania and Ohio. What we have worked on in Ohio is through our Ohio Department of Transportation getting a standard road agreement together, because the one thing the industry was facing was going from township to township or county to county, and people wanting a lot of different things, and that was hard to address that. So our Ohio Department of Transportation took the lead in working with the counties and the townships to develop kind of a standard road agreement that everybody can use and everybody can work with, but it is being addressed, I know, in Ohio and Pennsylvania very proactively.
Yeah, this is Bill Ritter. I would agree that that's happening in most places around the country. In places like Colorado, where there are vast public lands that have shale gas underneath them, and also vast sort of open lands, ranches and farms, the industry is also looking at how they, at the end of the day, reclaim that land and try and take it back to its sort of original state, and that even includes some of the roadways in. It's a really important consideration for folks in places, in rural areas or wide open areas. We're having a natural gas symposium next week, 3 days, where we talk about all the issues that we've talked about in this phone call today, but we're spending an entire session on looking at the importance of land reclamation as a part of natural gas extraction.
Okay, well, very good. I think with that, we should wrap up. First, I'd like to thank everybody for their participation. We really welcomed you being part of in the audience today. We're proud to represent the American Academy of Environmental Engineers and Scientists in this webinar. We hope that you have all found it to be interesting and informative. We weren't able to get to all of your questions. Thank you for submitting so many questions. I wish we had more time to answer and address more of them. But with that, I think we should close, and I would like to, in closing, thank our speakers in particular, because all of the speakers volunteered their time and obviously spent a great deal of time preparing for this, provided really wonderful input. And it's this kind of interaction, I think, that's going to help us as a society accomplish the kinds of management that will be necessary for us to successfully and safely develop energy technologies now and in the future. So thank you very much, and what we'll do now is turn it back over to you, David, for some housekeeping.
Yes, and that does wrap up today's U.S. Clean Energy Challenges Focus on Hydraulic Fracturing webinar, sponsored by the American Academy of Environmental Engineers. In just a moment, an online program evaluation will appear on your screen. Please take a moment to fill it out. Your feedback will help us to continue to bring you future quality programming. Today's program is copyrighted in 2012, American Academy of Environmental Engineers, all rights reserved. Thank you for joining us today, and enjoy the rest of your day.